Hi everyone, good afternoon. I'm Christina Daly from the Department of ECE, SNS College of Technology. In this lecture series, we are going to discuss about the quadrature amplitude modulation. Already we have discussed about the various types of the digital modulation techniques. Before going to see this, we have to know what do you mean by quadrature amplitude modulation. Here we are having three stages in the QAM. It is known as dual carrier modulation and the combination of amplitude shift keying and phase shift keying. The next one is the symbol transmission. Suppose if we want to modulate two carriers, that is in phase and quadrature, we have to keep that in 90-degree out of phase, and it combines both shift keying in order to encode the data, and what is the symbol that has been transmitted is multiple bits, and the purpose of this to enhance the data throughput. Where we are using this QAMS in wireless communication, that is Wi-Fi. So we are going for the various modulation schemes. Suppose if we are taking the advanced Wi-Fi protocols, so we are having the Wi-Fi 7 or Wi-Fi 6. And suppose if it allows 10 bits per symbol, automatically it will be in the form of faster wireless speeds, and we are using this in cellular networks. It is the throughput data transmission in 4G as well as 5G mobile networks, and it will support the multimedia and high bandwidth applications. So these are all the applications that has been used in the quadrature amplitude modulation. The main purpose of the quadrature amplitude modulation, it is essential for both efficient bandwidth utilization and it will deliver the reliable multimedia services. So where we are using means the digital TV channels, the high data rates, and the integrated services. So we are using for the high definition video and high speed internet access, and there will be 256 QAM is used to achieve the high data rates, and we are having the multiple digital television channels that will exist the coaxial cables. So where we are using this in optical fiber systems means the first one is the high bit data transmission and emulated QAM, and here we are using in the Shannon limit. So suppose if we are increasing the deployed high bit data rate for the long distance, or if we want to enhance the spectral efficiency, we can go for QAM, that is 16 or 64, and the data throughput, we can enable the data related to this Shannon limit. So these are all the advantages. There will be flexible modulation orders. It will support the various modulation orders, and the performance balance will be is to adapt the diverse channel conditions, and the QAM transmits more bits of data, and it will be used in the available spectrum. So this is the difference between the analog QAM and a digital QAM. In analog QAM, already we have used in the previous state. In digital QAM, where the zeros and ones that has been used, we are facing lot of challenges. The signal to noise ratio is very important in this QAM, and it is used for the accurate decoding, and it is highly sensitive to the impairments such as noise, non-linear distortions, and the synchronization errors. And what are all the solutions we have find out means it will help in the channel estimation, and there will be accurate phase, and it will ensure the reliability. The final thing is it will maintain the performance. These are all the things we are going to meet out in the future demands. It is used as a fundamental technology, and it will enable higher data rates, and it will integrate some generation communication standards. These are all the assessment questions. In QAM, both the amplitude and phase of the carrier is varied by the parameters. What are all the parameters we are using? And for example, if we take an 16 QAM system, 4 bits of data can be transmitted. Thank you.